Welcome back again on Friday mornings seminars for the IP. So I'm very pleased to introduce you to Richard de Grijs. I've known him for a number of years now, especially through IU activities. I will tell you briefly about it in a moment. So Richard, education was in Holland. He was a PhD in 1997 in Groningen. And then he moved to, as you will see, he moved around a lot. And then he got a professorship at the University of Sheffield in the UK in 2003, if I remember correctly. And then he was eager to move again, so he moved to Beijing. So this was a big move in 2009. And then he went to Peking University. You know, this is the Chinese subtleties of having Peking University for exposure to the world, and then Beijing as a city. It's typically Chinese, I would say. Anyway,
it's a historical leftover.
Yeah. So he stayed there for a number of years and developed many collaborations. You see many Chinese names here for this time, and this is where we first met, because he was very active in the organization of the IU General Assembly in Beijing in 2012. So since then, Richard has moved to other places. Now he's based in Macquarie University in Sydney, in Australia. And then beyond doing science, he's been very engaged in other activities. He's been, or he still is, editor for the APJ. And also he is very engaged in the IU educational activities. He's currently vice president of Division C, which is a big division entitled Education, Outreach and Heritage. This was a sort of outgrowth of the division reform, which is very successful. And Richard has established a node of the Office of Astronomy for Development, which is based in Cape Town, South Africa. And he's been establishing a node for East Asia in Beijing for a number of years. So that was extremely interesting and very positive for IU exposure in this part of the world. And so he's now vice president of this division. So next president, he will be incoming. And then before that, he was president of a commission on stars and clusters. And here we move into science. I will not summarize his scientific career. I'm not an expert in this field to start with, but just to say that overall, viewed from somebody like me, it's stars and galaxies. You know, the interplay between what can stars tell us about galaxies in many different environments. And now so he's going to talk to us today about the not so simple stellar population. So you see, you think that it's simple, but it's not so simple, although the summary suggests that it's back to simplicity, perhaps, in a way. We'll see, he will describe that. So, okay, so it's not so simple stellar population in nearby massive star clusters. Richard.
Thank you, Thierry. And thank you, Thierry, and also Michel for the invitation to come to IAP today. I had a meeting in London for the last few days, and coming all the way from Australia to London for 2 days seemed like a bit much. And so I reached out to some colleagues, and as Thierry said, I'm from the Netherlands. I'm going with my wife to the Netherlands tomorrow, see my family. Next week, give a few more talks in the UK, and then fly back to Sydney. I moved to Sydney about a year ago. I spent 8.5 years, as Thierry said, at Peking University, the Kavli Institute for Astronomy and Astrophysics. And then they offered me a position as Associate Dean at Macquarie University. So I'm now responsible for the international relations of an entire faculty of 10 departments. That's a lot of admin. I'm supposed to spend 60% of my time on this, but in practice it's more like 80%. Nevertheless, I work very closely with a lot of students and postdocs, mostly from China at this point still. And as you can see, these names are all junior scientists from China, except Chongyuan Li, who is a postdoc at Macquarie University. He was my PhD student, possibly the most successful PhD student I've ever had. He wrote 2 first author Nature papers during his PhD. So that was quite amazing. He's a great guy. He just got an offer for a staff position at a good university in China, and he'll be moving there next month, actually. The only senior guy on this list is Li Deng. He is my best friend in China. He's a professor at the National Astronomical Observatories. And together, we have successfully led to completion about a dozen PhD students and a whole army of undergraduates. And so this is, this is my pipeline of students doing all the hard work and getting fantastic results out. I just want to highlight one thing. If you've read the science news in this last week, you may have seen a lot of news about a warp and twisted Milky Way disk. That's one of my postdocs. And so I was the only non-Chinese scientist on that Nature Astronomy paper. My life has been so busy for the last week because I've had calls from journalists several times a day, almost every day. But it's been fantastic. If you haven't seen it, just search warp and twisted Milky Way disk and you'll find the story. Right, so today I'd like to talk a bit about the most recent results from my group about star clusters. I've been working on star clusters ever since my first postdoc in '97. Here is a family portrait of these star clusters. Now, my group has been interested for a long time in the evolution of star clusters. That means from young to old age, particularly of massive clusters. Massive, more than a few times 10 to the 4 solar masses. Now here's a very nice family portrait of star clusters, most of them in the Milky Way. An example of what massive clusters look like. The problem with massive clusters in the Milky Way is that they are all old. They are 10 gigayears old or older, right? Those are the old globular clusters. Beautiful images here, mostly with the Hubble Space Telescope. We can resolve individual stars. We can work out what they do and what they are, what their metallicities are, what their masses are. But it's a single time step. There is no evolution in there. Now, there are some massive younger clusters in the Milky Way. One of them is visible up there. That's NGC 3603, which is a few million years old, but it's only about 10 to the 4 solar masses, so it will not survive to become an old globular. It will dissolve before it reaches any serious age. So in order to study massive younger clusters of different ages, you need to go outside of the Milky Way. You need to go to the nearest galaxies, the Magellanic Clouds. And here are two examples of somewhat younger, 100 million years or maybe a few 100 million year old star clusters, massive star clusters in the large Magellanic Clouds. They tend to be a few times 10 to the 4 solar masses. Now, why do we care? Well, star cluster science can be used for a whole slew of scientific applications, from large scales to small scales and everything in between. On large scales, star clusters tend to be formed in the most violent environments where the highest pressures are. So by using star clusters and using their ages and physical properties, we can follow the evolution of their host galaxies, particularly the most violent evolution of starbursts and interactions with other galaxies. On much smaller scales, star clusters contain hundreds of thousands to millions of stars, and they were all formed roughly at the same time. So we can really use them to study stellar evolution and stellar properties and all kinds of stuff like that. That's the focus of this morning's talk. I'll tell you a lot more of what we can do with individual stars and star clusters and what that is going to tell us about stellar evolution and star clusters as such. And then there's a range of other things we can do. We can, yes, theory of stellar evolution, dynamics, radiation fields, even planetary system formation. This is where our N-body friends come in because we cannot see planets in star clusters. It's too far away. Now, those of you who are not stellar physicists, I'd like to share with you a brief animation of how we go about studying stars in star clusters. This is based on Omega Centauri, the most massive compact cluster of stars in the Milky Way. I'm reluctant to call it a star cluster because it might be the core of a dwarf galaxy. That's what it looks like, blue and red stars, very nice. You can split that up into colors. That's what's going to happen next, I assume. Right, so we're splitting it up in colors. That's in essence splitting it up in temperature or perhaps metallicity of the stars, with the hottest stars on the left and the coolest stars on the right. And then we rearrange it by the masses of the stars and we get our Hertzsprung-Russell diagram. Right? This is the main sequence. For those of you working on galaxies, that's a different main sequence from the galaxy main sequence. This is where stars start their life and spend 90% of their lifetimes. They turn off the main sequence here, get onto the subgiant branch, the red giant branch. These are red giants, and then eventually go over to the horizontal branch and the white dwarf sequence. I'm showing you this because I'm going to use a Hertzsprung-Russell diagram like this as a diagnostic tool to explain what we've been working on for the last decade or so. Now, I talked about simple stellar, not so simple stellar populations in the title of my talk. That means there's something that we understand as a simple stellar population. Now, here is a diagram that is a pretty good representation of a simple stellar population. We believe that a simple stellar population is formed of stars that were formed at the same time, right? Roughly, massive stars and low mass stars have a lag of about 10 to the 4 years or so, but that's minor. They all formed roughly at the same time, and that means that they have a sharp and narrow main sequence turn off there. They also formed from the same progenitor gas cloud, because they formed at the same time, at the same location, right? Same progenitor gas cloud. That means they have the same chemical composition, which we usually approximate by the metallicity. How can you tell that in a diagram like this? The features here, particularly the main sequence and the next features of stellar evolution, are narrow. There's no width, because if there were a metallicity spread, you would expect a width on the horizontal axis, which is color, but that's equivalent to metallicity or temperature. The only thing that changes here is the mass range, with the lowest mass stars being down there. This would be about 0.1 solar masses, the hydrogen burning limit, all the way up to the main sequence turnoff. This is a composite of 5 old galactic globular clusters, so that turnoff would be probably 0.7, 0.8 times the mass of the Sun. So this is your mass range. Beyond that, stellar evolutionary phases are very rapid, and you don't have sensitivity to masses anymore. So this is just anything 0.7, 0.8 solar masses and upwards. Well, roughly that mass. The problem with simple stellar populations is that they are defined only for single stars. And that is a big problem, because we know that most stars in the universe form in binaries or higher order multiples. And you can see that already. Look at those stars. They're not supposed to be there. Simple stellar population would be main sequence turnoff, which gives you the age, and then subsequent evolutionary phases. These stars look younger than the rest of the main sequence, so they shouldn't be there. These are called blue stragglers, and I'll talk about blue stragglers at some length in the next few slides. In addition, those of you who are observers might say, oh, this is not so good because there are some uncertainties there. This is not due to uncertainties. These are real stars, and they are binary systems. They are binary stars, 2 stars, seen in the same resolution element, but which cannot be separated from each other, and therefore they are brighter than a single star of the same spectral type. Brighter means higher luminosity or lower magnitude, and that's why they sit above the main sequence. That's what binaries do. You can actually model that very well and work out binary fractions by modeling the fraction of points above the main sequence. So that is the idea of a simple stellar population, but even here already you can see some of these deviations related to binary systems. The binaries here, and the blue stragglers, which are also related to binary evolution. Now, a decade ago, this whole idea went into the dustbin, because we had observations like this of many star clusters. This is a cluster in the Large Magellanic Cloud, fairly tight main sequence. There's some scatter up there that might be binaries or observational uncertainties. But then there is this huge spread at the main sequence turnoff, which would imply more than not just a single age of stars, or possibly something else. We had this old galactic globular cluster that didn't show just 1, but maybe up to 3 main sequences. And we had this old galactic globular cluster that didn't show just 1, but 2 subgiant branches. So out of the door went the idea of simple stellar populations, and everything became more complex. We thought we understood star clusters about a decade ago. At the moment, we're not so sure anymore. Right, so now I'd like to focus on a number of these features that are weird and wonderful, that deviate from the simple stellar population idea. And I'd like to start by looking at blue stragglers. As a reminder, blue stragglers are sitting there. They were first found by Alan Sandage in 1953 in the galactic globular cluster M3. And he found them in the outer regions of this globular cluster. At the time, that didn't raise any issues, but now we think that's very weird, because blue stragglers are binary related, and therefore we expect them to be found in the cluster centers. So M3 was a bit special. For many years, astrophysicists discussed vigorously what may cause the formation of these younger-looking stars in an older star cluster. And many ideas were put forward, but eventually two types of blue straggler formation lasted, and these are both binary related. You can either have collisionally induced blue stragglers, so two low mass stars collide, they form one single object, and eventually that turns into a blue straggler star. In essence, what happens is that that material from the interior of the star goes to the outside, and so the outside starts to look younger, in that sense, bluer, and that's why these stars look younger than they actually are. So these are rejuvenated stars. A second idea of forming blue stragglers is through coalescence. Stars in a binary system orbiting around each other, getting closer and closer and closer until they finally coalesce into a new, more massive system that turns into a blue straggler. These are the two scenarios that are left from an initial 10 or 15 different scenarios that people have suggested over the years. So we believe that blue stragglers formed in two different ways, through collisions and through coalescence. And it seemed a couple of years ago that this was borne out by observations as well. Francesco Ferraro from Bologna University published this plot in Nature for M30, one of the globular clusters in the Milky Way, where he saw very clearly a sequence of bluer blue stragglers that was quite tightly bound, with a gap in between, and then a distribution of redder blue straggler stars. And he said, well, thinking of the two scenarios that may have formed blue stragglers, we believe that the collisional blue stragglers may have formed at an extension of the main sequence, just like that. And these stars are formed from binary systems that are in the process of transferring mass from one to the other and eventually merging into a blue straggler. Now, of course, in nature, you don't get these nicely colored blue and red data points, but even if you look at the raw data, there seems to be a clear gap between those two populations. Now, the idea, of course, would be then, may I leave the answer to that question to my next slide, right? Because you will see it there. Because I don't know it here. This is nature, so nature, it's just flashy results. Pardon? So the idea is you can actually test this idea, and by considering where you would find blue stragglers formed in either of those two ways, right? Because where would you get most collisions? Where the density of stars is highest. Where is the density of stars highest? In the cluster centers. So you would expect those collisionally induced blue stragglers to be located in the highest density cluster centers, and the mass transfer blue stragglers in the outer regions. That's what we did for another cluster, but here you see some of the error bars, right? This is work by Cheng Yuan, who at the time was my PhD student. Now, this is not as clear-cut as in that Nature paper. We looked at a cluster in the Large Magellanic Cloud where we found 115 or so blue stragglers. And then we looked at objects that were very close to the cluster center in red, and objects that were located at great radii in the outer cluster. And we then said, well, look, there is a statistical difference between the distribution of red and blue data points there. This is Hubble Space Telescope data of an LMC cluster. Yeah. So we kind of supported that idea, but it wasn't as clear-cut. We've since looked at other blue straggler distributions in LMC clusters, and it seems to be borne out as well. So most collisionally induced blue stragglers form in cluster centers, while mass transfer coalescing blue straggler stars form pretty much anywhere in the cluster. We took this recently one step further. We said, okay, we're interested in the properties of these blue stragglers. And so my current student, Weijia Sun, who's still at Peking University, he looked at an object at about 24 star clusters in the Large Magellanic Cloud, and he defined the blue stragglers, which are clearly offset from the bulk of the population. But he said, look, these blue stragglers in slightly older clusters, older than a few times 10 to the 8 years, may have evolved off their main sequence, because this is in essence an extension of the main sequence. They may have evolved off, and they have gone over to the right-hand side of the diagrams, where they are the equivalents of younger red giants. Now, how do you distinguish that? You have to do that statistically. So what we do here is this is the fit to the main sequence of the cluster at a younger age, following the blue stragglers. So this is the main sequence. That would be the main sequence turnoff, subgiant branch, red clump area, and red giant branch. We do the same thing for the bulk of the stellar population. That's the red line here. And we can make a distinction between stars statistically associated with the red line and with the blue dotted line. And so those green stars here are what we believe are evolved blue stragglers associated with this population. That was the first that someone considered evolved blue stragglers. And you will see that this is actually an important consideration to take into account, that blue stragglers are not just newly formed stars, but they also evolve in their host clusters. Because at the time, work by Lee et al. Showed that if you, in galactic globular clusters, if you relate the number of blue stragglers in a globular cluster to the mass of the core of the globular cluster, there seems to be a correlation here. It's a power law with a slope of 0.5. And so we thought, well, maybe we can do the same for clusters in the Large Magellanic Cloud, and the difference being they are much younger than the galactic globular cluster. So perhaps this tells us something about evolution. This was purely a fishing expedition, but we decided to do it. So here is core mass versus number. In gray in the background, you see the galactic globular clusters. In different colors, you see the clusters in the Magellanic Clouds. And if we simply use, and you know, I would not fault you by saying, look, these are not very good fits, but you try to fit a straight line to a mess of data points. That's what the student did, actually. Sorry, I should not blame him. I condone that, of course, being the supervisor. And so if you just make a fit to the data points of the blue stragglers in the core versus core mass, you get this fit here, which has a slope of 0.66. And I remind you, this slope was 0.5 for galactic globulars. But if you then take into account the evolved blue stragglers as well as the core blue stragglers, or the young ones, and you fit a slope, you get a slope that's pretty close to that 0.5. Now, what does that tell us? I mean, yes, we find this, yes. I'm not sure if they do not find them, but they haven't looked for them, so they have not published them. So this was, yeah. So what, I'm showing you some data, but why is this important? Well, what we can do is we can make plots like this. What we've done here is we have normalized our parameters by the mass of the cluster, assuming a benchmark of 10 to the 5 solar masses. In this plot, we plot the annual collision rate, so many collisions per year, versus the number of blue stragglers in the core. And we expect, if there is simply disruption of binary systems, that the distribution should follow this dashed line. So it seems, and this applies, this distribution seems to fit our data fairly well for both the core blue stragglers, the young ones, and the young plus evolved ones. So what does that tell us? Well, we compared our results with predictions from n-body simulations, where we used two different ways of forming blue stragglers. One of them just from binaries, coalescence and disruption, where you expect the distribution to go down this way, and one of them from collisional formation, where you expect this whole parameter space to be filled in. Now, clearly, the left-hand side seems a better representation of our data, and our data is not really conform the data on the right-hand side. So we concluded, based on an analysis of these data points, that most of the blue stragglers we find in the Large Magellanic Cloud star clusters were most likely formed from coalescence and not from collisions. So that was, yes? I didn't hear what you said. We do find mass segregation in these clusters. Yeah, we did that kind of work 10 years ago. Yeah, we do find clear mass segregation even in young star clusters, as young as a few times 10 to the 7 years. I published that in 2002. Now, I would like to move on, but stay with the blue stragglers, because blue stragglers are usually defined as stars that are bluer and brighter than the main sequence turnoff. But there is no reason for stars that that coalesced or collided to be as bright as or more massive than the main sequence turnover. That can happen on the main sequence as well. And so we said, well, can we find blue stragglers that are still on the main sequence? One of my other students, Yuzhao Yang, she started looking at this particular cluster. This is NGC 1851, I believe. This is the color magnitude diagram. And you see there is a scattering of data points all around that main sequence. Now, I mentioned at the beginning that if you have lots of binary systems, they tend to be brighter than single stars, and they sit above the main sequence. So we believed that scattering of these stars, at least those stars that were not associated with error bars, were simple standard binary systems. But what about these objects at the bottom there? And so what Yu Zhao did is she looked carefully at the spatial distributions of both these stars and those stars. And so she made a selection box, and then she found that the standard binaries, the red line, this is radius, distance from the cluster center versus population ratio. The standard binaries decrease in the fraction of binaries decreases from the cluster center to the outer regions. While this blue distribution, those are the stars down there, increases from the cluster center outwards. So we did some simulations, and we thought about what we might be seeing here. And what we believe that we're seeing here is that we have lots of binaries in the cluster center and fewer in the outer parts. But in the outer parts, we have more of these blue stars. So we believe what we're seeing here is the conversion of binary systems to coalesced systems as a function of radius in the cluster. And so that was the conclusion of this work. Now, this is the PhD work of Yuzhao Yang. She's done a few more clusters so far, and we find similar behaviors in other clusters as well. So this is a new idea that blue stragglers also form along the main sequence, and you do actually see the evolution of binary systems into blue stragglers in the act, which was, we thought, quite cool. Now, a few other things I would like to address. Most data of star clusters, Hubble Space Telescope data of star clusters in the Magellanic Clouds looks like this. These are color magnitude diagrams for two 10 to the 8th, few 100 million year old star clusters. And you can see a few things. You can see that the main sequence is not very tight, and the main sequence turnover is not very sharp. And so many ideas have been put forward that could explain the spread in the main sequence turnoff and the spread on the main sequence. And here are some of the ideas. The broadening of the main sequence turnoff could be due to differences in helium abundances, binary populations, a range in stellar ages or metallicities, that's degenerate, you cannot really tell, or a population of rapidly rotating stars. Now, if you had stars that were more helium enriched than the cosmic helium abundance, they would be bluer than the bulk of the population. While our extension of the main sequence turnoff goes to the red. So that is something that doesn't make sense in the context of these broad extended main sequence turnoffs. But we have binaries, we have stellar ages or metallicities, and we have rapidly rotating stars. So based on a distribution like that, how do you go about determining which of these scenarios is important? Well, you can try to be a bit smart and say, well, if we look at the main sequence itself tells us how many binaries there are, or the fraction of binaries in this star cluster. The only assumption you have to make is that you can apply a binary fraction you get from the main sequence to the entire cluster. In other words, that all spectral types have pretty much the same frequency of binary systems. It's not an ideal assumption, but it's not too bad in practice. Then we can also look at the extent of the red clump. The maximum extent of the red clump tells you the maximum age or metallicity range that can be contained within a cluster. And whatever is left over, that's at your extended main sequence turnoff, and that might tell you what the fraction of stars is that's rotating at rapid speeds. So let's try and apply that in practice. Here again, we have these two color magnitude diagrams. I have now overplotted here the maximum allowable age ranges, assuming that the entire width of the main sequence turnoff in both cases is purely driven by a range of stellar ages. The youngest stars would cover the left-hand side of the main sequence turnoff. The oldest stars would cover the right-hand side of the main sequence turnoff. And so you get a maximum age range of about 300 million years here, and similarly about 300 million years there. That's the basic standard approach that people used to take about a decade ago, I think. However, if you then look at the red clump, you can clearly see that the blue and red models don't match the red clump there, although they do there. So here, in this particular case, the width of the main sequence turnoff cannot be 300 million years. It's simply too much to account for the smaller size of the red clump. I see that I need to move on a little bit. So let me then talk about the other aspect, stellar rotation. Stellar rotation becomes important for ages of a few times 10 to the 8 years, a few 100 million years. It's not important for very young clusters. This is a color magnitude diagram of a few times 10 to the 30 million year old star cluster. What we see here in blue is a non-rotating isochrone. And what we see in red is an isochrone of stars rotating at 55% of the maximum rotation rate. The maximum rotation rate is the rate at which stars break up because of centrifugal motions. And you can see there is no difference. But if we now go from 30 million years to a few 100 million years, you can see there is a difference between blue and red. No non-rotating stars in blue, stars rotating at 55% of breakup in red. There's a clear difference there. Why is that? Well, stars that are rotating rapidly can retain hydrostatic equilibrium at lower temperatures, and therefore they are cooler and redder. And that's what you're seeing here. And so at the very youngest ages of the previous plot, the difference in temperature is not enough to be seen in these diagrams, because we're talking about much brighter spectral or earlier spectral types. So stars that are rotating rapidly get redder, and therefore they can cause a spread in the main sequence turnoff. Now, if you want to model your star cluster color magnitude diagram with rotation, you need to put in some a priori distribution of stellar rotation rates. It does not exist. That's actually the work of one of my PhD students, to come up with a statistical distribution of stellar rotation rates in star clusters. It's hard to do, but he's working very hard on this. What we did have at the time that we did this work was the rotation rates of stars in the solar neighborhood, particularly of B-type stars. And it turned out there was a peak in the rotation rate at 15% and another peak at 55% of this maximum breakup rate. So we modeled our data. We started with a simple stellar population. We added random rotational velocities to stars more massive than about 1.2 solar masses. Below that, you get random motions, but no rotation. We added the representative fraction of binary stars to our cluster, which we could have determined independently. And then we added photometric uncertainties. So we had to compare our observations with simulations like this. Now, to make a long story short, that's what we did for our clusters. Here's an example. This is the color magnitude diagram. We squeezed together the colored area here along this line. What you see in these plots for our two clusters, the two clusters of a few 100 million years old, we have observed in blue and simulated in red. And in both cases, those distributions here match pretty well. So what we concluded is that the extended main sequence turnoffs we see in our intermediate age star clusters can be caused by a population of rapidly rotating stars. That was the start of this, of the work of my group in this field. However, then we got a breakthrough. We looked at this cluster, NGC 1651, a cluster in the Large Magellanic Cloud, where we found quite an extended main sequence turnoff, something that looked like a gap there in a very narrow subgiant branch. And when we saw this, Chung-Yuan and myself, we got quite excited about this and said, well, this implies that, so this difference between the extended main sequence turnoff and the narrow subgiant branch probably implies that you cannot have a range of stellar ages. Let's quantify that. So here again, this is the blue isochrone is the youngest stellar population you can have for this cluster. The red isochrone is the oldest one that covers most of the main sequence turnoff. And then what we did is we defined a sample of subgiant branch stars, and we checked statistically to which of the blue or red isochrones each of these stars belonged. And you can see, this is for both the core and the whole cluster, that most stars are associated with the blue isochrone and very few, if any, with the red isochrone. We did a separate analysis, a second analysis, where we took that same sample of subgiant branch stars and assumed that the location of every single star was purely driven by the age of the star, only the isochrone age. Then we took a random sample of main sequence turnoff stars and did the same thing. The position of every star at the main sequence turnoff only driven by the age. What are the age distributions you get? Well, for the main sequence turnoff, we got a broad distribution. This is log age. For the subgiant branch, we got a peaked distribution, and the two of them are statistically not the same. So the conclusion of this work was that an extended main sequence turnoff does not necessarily imply an age range, right? Because the subgiant branch implies an age range of no more than 80 megayears, while the width here implied more than 300 megayears, if it was purely age-driven. So that was an interesting conclusion. We follow that up. Here was another cluster. Oh, some people said, oh, but you know, what you can have in cases like this is you can have a range, you can after all have a range of ages, because these stars are, or these clusters are old enough to have generated asymptotic giant branch stars. Asymptotic giant branch stars have massive stellar winds. These stellar winds interact, and in the interaction regions you form new stars, and they are younger. So you can have an age range. So we looked at this object, NGC 411, has the most extended main sequence turnoff region known. If this is entirely driven by age, this is 750 million years of age range. Massive. Well, this cluster is only a few times 10 to the 4 solar masses in mass, as the lowest escape velocity of any of these extended main sequence turnoff clusters. In other words, if you have asymptotic giant branch stars with massive winds, the cluster does not have enough gravity to retain the winds, the ejecta. Right? So you cannot form a secondary generation of stars because the winds just disappear from the cluster. And indeed, that's borne out by the data. We have this massive extended main sequence turnoff. We have a single line, a single isochrone of subgiant branch stars. So age cannot be the driver of the extended main sequence turnoff in this cluster, nor, we believe, in other clusters. Then I had an undergraduate student, Xiaohan Wu. She absolutely brilliant. She did her undergraduate at Peking University. She started in her second year working in my group. At the end of the third year, she had an aptje letter. Then she went off to Arizona for a summer project. She got a paper out of that. She did her final year project at Tsinghua University, got another paper out of that. 3 papers at the end of her undergraduate degree. She's now a PhD student at Harvard University, so she's absolutely amazing. Anyway, and she came to me and said, can I do a project in your group? I said, well, we can look at another cluster. And here is one with an extended main sequence turnoff. Let's see what it tells us. But then we found something interesting. If you look at that subgiant branch, and I'm not sure if it's very clear, but it looks like the width of the subgiant branch is quite wide here and not so wide there. So we split up the subgiant branch in 2 equal sections in terms of numbers of stars, and we did what we did before. We assumed that the location in the diagram of every star was purely driven by its age. And so we got age distributions for the main sequence turnoff region, for the left-hand side of the subgiant branch, and for the right-hand side of the subgiant branch. This is a broad distribution for the main sequence turnoff. The blue subgiant branch also shows a broad distribution in ages. The red subgiant branch shows a sharply peaked age distribution. This is even more obvious if you include ultraviolet filters. Right? Broad subgiant branch that narrows down to the right. Why did we publish this as an aptje letter? Because this was the first observational evidence that we have rotational deceleration of stars when they go from the main sequence to the red giant branch. Right? When you go from the main sequence, you have a massive star like the sun, or maybe not so massive star, but you have a compact star like the sun. When these stars become red giants, they swell up. They become much, much bigger. Their angular momentum needs to go somewhere, or needs to be retained. So you need to change from rotation, from fairly rapid rotation to not very rapid rotation to retain that angular momentum. So we see here rapidly rotating stars to non-rotating stars. And so that was really cool. And we actually did some simulations. We could reproduce the observational data by assuming that more than half of the stars were rapidly rotating. That was a bit of an odd conclusion, but we don't really know what the distribution of rotation rates in star clusters is, so for the moment we leave it at that. But that's why it's good to know what the rotation rates are to see if that conclusion is realistic. In the final few minutes, I'd like to show you one more rather odd result that we found. I was in my office at Peking University, and Chong Yuan came to my office and said, "Richard, I found something really weird. This cluster." Again, he was doing this, he was finishing his PhD, and he was like, "Well, this broad main sequence turn off, narrow subgiant branch, yeah, we can do the same analysis as before. But look what I found, right? The star's here, and it looks like this is a sequence, and it looks like a secondary sequence. Let's fit some ages to the cluster." That's what he did. The bulk of the cluster, 1.7 gigayears old. And these two sequences, if you fit isochrones, you have 400 and 800 million year ages. So we said this is a cluster that potentially shows stars of 3 different well-defined ages. Well-defined because the sequences are narrow. I happened to be at the American Astronomical Society meeting a few years ago in January, and I ran into Leslie Sage, who is the Nature Astronomy editor. I said, "Leslie, we found this is very odd, and I think maybe this, what we're seeing here is the effect of gravitational oscillations, star clusters undergoing core collapse, forming blue stragglers and then expanding again. Do you think this is worth publishing or submitting to Nature?" And he said, "Well, yeah, it's interesting, but it's only one object. Can you find me a few more examples?" Now, I was based in China, so I had lots of students, and my students looked very hard through the Hubble Space Telescope archive and found 2 more clusters that showed additional sequences. And so Leslie said, "Okay, submit it to Nature." So what we concluded at the time, and I think that's wrong now, Nature is the journal of wrong results, or at least 50% is wrong, and we had 2 papers, and I think one of the 2 is wrong, so that fits my statistics, right? Anyway, what we concluded at the time is that these younger sequences may have formed from star clusters in the Magellanic Clouds moving through the gas-rich environment of those galaxies. Meanwhile, accreting through Bondi-Hoyle accretion, gas until the gas density reached the minimum threshold to form new stars. That's why you get them all at the same time. That was our speculation. I think that speculation is actually wrong. It doesn't work if you look at it in detail. But what might work is what my postdoc, Jong-Suk Hong, did a year later or so. He did n-body simulations to try and understand how we get clusters with multiple H sequences. And I won't go into the great details. I'd like to show you one of the ideas that we had, and that was to form these multiple sequences by merging clusters. And here's an example of that. Right? We have a massive cluster and a much smaller cluster that's merging together, and the merger timescale is roughly equivalent to the age of this cluster system. And so when you do that, when you've merged your cluster, indeed you form a star cluster with standard age stars, and then a younger population which are distributed in a similar radial distribution as what we found in reality. So what we now believe, and I can tell more about this later if you like, we now believe that, these younger sequences may indicate that this particular cluster, as well as the other 2 clusters here, were formed through the mergers of some clusters in the large and small Magellanic Clouds. That's not such a strange idea, because it's very well known that the large and small Magellanic Clouds contain many double clusters. And so this is this was a first exploration of what might have happened, but we believe that we're on the right track there. So having said that, let me give you the take-home messages of what I've been talking about so far. First, at intermediate ages, and we're talking here about 1 to 3 gigayears, extended main sequence turn-offs imply the presence of an age spread or a population of rapidly rotating main sequence turn-off stars. A simple stellar population, including rapidly rotating stars, seems to be the best match. So we go back from the not-so-simple population back to a simple population, as Thierry said in the beginning, but with the caveat that we need stars of different rotation rates. The presence of an extended main sequence turn-off, therefore, does not necessarily imply an age spread, and our most recent results suggest that we really need to rethink how star clusters form and evolve. So having said that, where next? There's a couple more projects we're working on with my group, particularly still Chinese students. Wei Jia is working on stellar rotation rates in star clusters. He's got fantastic SALT data that we got through a collaboration with the University of Canterbury in New Zealand. He just submitted his first paper on the SALT data, where we see indeed clear evidence in our spectroscopy of rapidly rotating stars in a number of open clusters in the Milky Way. We've been looking at metallicity constraints. Is there chemical variation or not? We believe that based on our observations of red giant branch stars, there is no metallicity variation, but there might be differences in helium abundance. I've got a new student who's about to start working on helium abundances in red giant branch stars. And Yu Zhao, the student who looked at the radial distribution of the blue and red binary systems, is working on using binary fractions as a function of radius as a potential dynamical clock of star clusters. So there's a lot more work out here that's related to what I've been telling you. I've tried to give you an overview of where we are. There's a lot that we don't know yet, but that's where we are, and thank you very much for your attention.
Okay, so now, thank you very much, Richard. So, questions? Yes?
No, this was pure N-body. We did not do gas. But in terms of these very young star clusters, the gas gets dragged behind, and in the end, you know, gas gets expelled from these clusters within 10 to 40 million years. Yeah, because you get supernovae that go off, and you get the massive stars that have these massive winds, and so yeah. So this is a time scale in millions of years, so that's much more than the 40 million, and that was the starting age of the simulation. Oh, in the clusters, let me go back to those. Here, a couple hundred million years. So at those ages, there should not be any gas left in star clusters. There is no evidence of gas in clusters older than than about 100 million years. This was work done a few years ago by Nate Bastian and his team from Liverpool John Moores University. So this is related to the idea of star cluster infant mortality, that you get supernovae that might or might not disrupt the cluster, but they happen on timescales of less than 40 mega years. We haven't found anything, no, that's right. But the problem one of the problems of doing this work is if you go to even younger ages, it becomes actually very difficult to distinguish between ages, because there the models are not so accurate, particularly less than 10 mega years. Michel.
Yeah, concerning the origin of this blue star, so we should have now perhaps high precision data about the velocities. If there are 40 binaries or ejected things like that, does one have data now?
I am not aware of that, no.
Because Gaia should give some...
Well, Gaia should...
Not velocities, but...
proper motions, right?
Motions, yes.
Yeah, and I don't think that's available yet.
That could be one thing.
My collaborator, Li Tsai Deng, is an expert on blue stragglers, so that kind of work is driven by his side.
And my other question is completely different. What are the arguments one has to suggest that the cores of some of these clusters are in fact cores of strict dwarf galaxies?
Oh, I mentioned that in the context of Omega Centauri. It's a number of things. If you look at the color magnitude diagram, the Hertzsprung-Russell diagram, well, some people suggest that there are 10 main sequences. I think most people, well, if you look at it, you can fairly easily identify 6 or sometimes 7 main sequences. So how do you form those if it's not a simple stellar population? So that's one thing. It's very massive. It's the most massive cluster-like object in the Milky Way. Its radial distribution is not a king profile, as you expect for old globular clusters. It's not radially truncated. So all of these arguments suggest that Omega Cyn may not actually be a globular cluster, but a stripped core of a dwarf. NGC 2419, I believe, is another example. And G1, the cluster associated with Andromeda, may also be the stripped core of a dwarf galaxy.
Yeah, something I don't understand. You say that the stars that are above the main sequence, okay, on the right side, that they are more luminous than main sequence stars. So what makes you think, how do we know that they are more luminous rather than redder? Because
well, if they're formed through binary evolution, then you have...
Sorry?
If they are formed through binary evolution, you have two main sequence turn-off stars that merge or coalesce together, and so you've got more mass and therefore more luminosity, right?
No, but this is the interpretation. But what makes you think that these stars are more luminous rather than redder? Observationally, I mean. You have points on the right side, and then you can either believe that they come from low mass stars and they are more luminous, or you can also believe that they are redder relative to stars which should be more massive in this case.
Well, if we don't do any interpretation, but we just look at the data, anything that's sitting above this line is more luminous than the main sequence turn-off. That's simply the data.
No,
this is high luminosity, this is low luminosity.
I'm talking about stars which are in the main sequence, okay? Below, much below. So you have stars that are above on the right side, and stars that are on the left side. So.
I don't understand your question.
Okay, doesn't matter.
Sorry.
Yeah, this should be discussed perhaps between you two later. We need a pointer for the audience also, perhaps.
I was just wondering, if there is an age spread, then how much is this age spread in star clusters that are not considered as single star populations? So is there a limit of how...
I can give a... Okay, let me say this. If you look at simulations of open clusters that start from hydrodynamics and form... Hang on, I'll get to your point. You know, at the time of star formation, there is a lag of about 10 to the 4 years between high mass and low mass stars. That's the first thing. That's the minimum lag, minimum age spread. But if you try to constrain it based on the simulations, and we did that, where are we? Anyway, not here, sorry. I can't, yeah, here. We did that here. We looked at the spread that we could find here, and we had a maximum allowed spread of 18 megayears. That was simply driven by the uncertainties in the distribution. Right? And that was based on the subgiant branch. If you then say, well, this is an age spread, it's anywhere between 300 and 700 megayears. But that doesn't seem to be supported by the other evolutionary features.
And what are the typical ages for these star classes? You have this age limit range?
Say that again?
What are the typical ages for these star clusters?
Oh, all of the clusters we've been looking at have ages between 1 and 3 gigayears. Mm-hmm. Yeah, so they're intermediate age. I should have mentioned that. Thank you.
Thank you.
Hi, so this is probably a naive question because I'm really outside the field, but I was wondering, you were mentioning one of the differences between your isochrones was either a spread in age or a difference in initial rotations in the stars, correct?
Yeah, these are plausible scenarios.
Okay.
Yes.
And so I was just wondering, have there been any attempts to do Muse observations or IFU observations of star clusters? I mean, I have no idea if this would be possible, but to get information on the rotation as well as the photometry.
Yeah, it's a very good question. This is what we've been trying very hard. The problem is that all of these intermediate age star clusters are based in the Magellanic Clouds, very far in the south. You need 0.3 arcsecond seeing or resolution for extended periods of times to do it. And so, while you can get 0.3 arcsecond seeing from Paranal, it's impossible to get observing time from ESO based on those constraints. We've tried, Thomas Puccia has tried, Nate Bastian has tried, lots of the teams competing in this field have tried, but the conditions are simply not there to offer the kind of data that we need. That's why Weijia, my student who's trying to characterize rotation, he's using SALT, but he's gone to open clusters in the Milky Way where we can resolve the stars more easily.
Okay.
Yeah. No, you can't. No, seriously, we looked at that. We tried it with Muse and adaptive optics, but even with adaptive optics, you need good seeing to actually get down to that 0.3 arcsecond resolution.
Hi. Yeah. You've mentioned that these clusters have ages in between 1 and 3 gigayears, but you were also mentioning before that you already studied some young clusters with few megayears, if that's correct. Can you comment a bit on those young clusters that show also this age spread?
No. Okay, you're confusing two things, and maybe I did not explain it well enough. These age spreads tend to occur at ages between 1 and 3 gigayears only. In the very young clusters, we do see extended main sequences, but not main sequence turnoffs, because there is no clear main sequence turnoff. And these extended main sequences are, in essence, defined by binary fractions.
Yeah. Any other question here? I may have one. Just bearing on the IMF. Is there a connection between the IMF? Could you see evidence for different IMF from cluster to cluster, and in addition to rotation, things like that? Or do you think that, from a point of view of the formation,
so a couple of years
the IMF, you would find something which is standard, and everything else is just a matter of rotation and dynamical interaction and so forth, but that initially everything is okay in terms of IMF, because there's now increasing evidence for different IMF in different environments, in galaxies, in the Milky Way and beyond. So I don't know how sensitive this kind of work is to the IMF, or is that something assumed in the first?
Rotation, in the way we can see it, occurs at masses greater than 1.2, 1.5 solar masses. There, the IMF is fairly well established, so the issue is at the low end. And a few years ago, we actually looked at that in some of our very young clusters in the sample, the ones that the lady behind you referred to, but that I didn't show in this talk today. And there we found that going down to 0.3 solar masses, the IMF in these two clusters that we looked at in the Large Magellanic Cloud was not appreciably different from the Chabrier or the Krupa IMF. But that's two clusters, and they were 0.4 solar metallicity, and perhaps that difference between that particular metallicity and solar metallicity was not sufficiently large for metallicity to have an effect on the IMF. But that's where we stopped, because we simply didn't have any better data.
Okay.
So what did you say, Michel? So the IMF is by looking at the population of stars down the main sequence, and then you also talked a lot about the spread of the main sequence, where you can you can guess the binary fraction. So my question is, do you have good evidence that the binary fraction is independent of mass, and is it independent of a globular cluster, and what are the typical values?
I just took those slides out of my presentation yesterday on the train to Paris. Right, so binary fractions can be determined based on color magnitude diagrams by looking at the spread on the right-hand side towards the red of the, right? Even with the Hubble Space Telescope, we can only look at binary fractions for mass ratios greater than 0.55, because for lower mass ratios you get blended with the single stars. At those mass ratios, the mass ratio distribution, which is governed by a parameter alpha, doesn't actually matter so much. We looked at that. So it doesn't seem that there is a large dependence on mass of the stars. That's the first point I wanted to make. Now, binary fractions in these very young clusters tend to be, we're talking F stars, F and G stars, tend to be 60 to 70%. That's high, but it's not so different from the binary fractions of fairly young stars in the field. In old globular clusters, binary fractions are in the single digits because of 15 gigayears or 10 gigayears of dynamical processing. Does that answer your question? Yes. Yeah. Okay.
Yeah, just a last point, perhaps as a conclusion. What Richard didn't say that in his university, he's in charge of international affairs. And one of the reasons he's here is that we want also to discuss possibilities for extended exchanges between Pierre and Marie Curie, now Sorbonne University and his university, for young people to have part of their PhD there, for postdocs or even for senior people. So keep it in mind. We will be discussing the practicalities, but there will probably be possibilities to have stronger relations between the two universities for all of us. Not necessarily on globular clusters only. Don't worry about that. So thanks a lot, Richard, for your visit. It was a pleasure to have you here.